The speaker is Professor Meng Wu from the University of Seoul, and the title is The Intersections of Dynamical Cantor Sets. So let's welcome.
Thank you for the invitation. So it's a pleasure to speak here. So I have supposed to talk about some topic about intersection of Cantor sets, and most specifically about a conjecture of Fürstenberg about intersection of times 2, times 3. Yeah. So by now it's like that's already been like several years. So there are several conjectures of Fürstenberg about this kind of rigidity properties of times 2 and times 3 dynamics. So probably the most famous conjecture about this in this series is this so-called times 2 times 3 conjecture about invariant measures under these maps. And another very, very deep conjecture is this, we can maybe call it orbit conjecture. That's about expansions of numbers in base 2 and in base 3 that we will talk about a little later. And the main focus of this talk will be the intersection conjecture. That's a conjecture about the dimension of the intersection of Cantor sets, which are invariant by 2 and by 3, respectively. And then there's another conjecture. That's the sum set conjecture. That's about the dimension of some sets of Cantor sets. So that's the sum set conjecture has been proved some years ago by Bablu and Mike Hoffman. In this talk, we will mainly talk about these two conjectures. So these two, the first one is still open, and the second one is also open. Actually, it's very much open. But the last two, it's now solved. Okay, so study the intersection of Cantor sets with independent symmetry. So here, the symmetry just means the arithmetic expansions. So that problem was initiated by Fürstenberg in the late 60s, and actually one of the motivation was try to study about the complexity of orbits of real numbers, for example, in different bases, or more generally about the orbit of points in dynamics. With respect to different dynamics. Okay, so since this expansion of numbers in different bases is more, I think it's more accessible. So I will start with the orbit conjecture. So in our daily life, we use decimal to expand numbers, and in computer science, we use binary. So these are two examples of how to express numbers in different bases. So actually, it's a fundamental problem, and actually, mathematically, we know very, very little. Is how does the digit sequence of a number is related to its say its algebraic or analytic property. So, for example, the expansion of digit expansion of the algebraic numbers which is believed to be like should be like quite random, but that's just a conjecture, and it's really difficult to study this kind of problem. So for example, for those numbers like some classical constant, it's really completely out of reach to get a satisfying understanding of the expansion of those numbers. Yeah, so here's a famous example. Is this pi? So if you Google pi on Wikipedia, you will probably find like probably more than 20 different expressions of this number. So I mean, you can find all this kind of very nice, very beautiful analytic expression for this number pi, but actually we know very little about, I mean, mathematically about the digital sequence of pi. So here it's like, I think it's 200 decimals. So numerical computation shows that the expansion, the digital sequence of pi behaves very randomly. But theoretically, try to prove that it is random, it's really hard. Actually, we don't even know if, for example, the digit 0 will appear infinitely often. Well, of course, because this is a irrational number, so at least the 2 digit will appears infinitely often. But we don't know if, for example, if 0 and 1 will appears infinitely often. Okay. Here we talk about randomness. So in mathematics, one way to define this randomness of a digit sequence is, for example, I mean, in dynamics system, we can define the complexity of a number by first look at because the digital sequence of this number is closed. I mean, it's just the coding sequence of this number under the times 10 map. So if you look at the orbit of this x by the times 10 map, and then look at the orbit closure. Okay, so this is the orbit, and this is the orbit closure. So then you can talk about the dimension of a set. So here you can take, for example, if you are familiar with, you can talk. I mean, yeah, you can, for example, take the box dimension of this set, and then define the complexity of x in base 10 to be this number. Okay. Yeah. So this is the complexity of a number in base p, for example, and yeah. So this is some either fact. So if x is a rational number, then since the orbit will be finite, so in this case, the problem is trivial. So the complexity is 0. But for general, and especially for a given individual number, this is in general quite complicated to know the precise complexity of that number. So this is a hard problem. So then how about if we turn the problem a little bit and look at the expansion of numbers in 2 different bases, say. Okay, so it sounds like, okay, so you cannot understand the problem in one basis, why you should bother yourself to look at it in 2 different bases. This sounds like makes the problem more difficult, but it seems that this is there's some interesting phenomenon here. Okay, so in this case, if the basis, so say p and q, so you want to look at the expansion of number in base p and base q. In this case, you have 2 different situations. One situation is when this log p over log q is a rational number. In this case, P and Q called dependent. So like when P is equal to 10 and Q is equal to 100, then in this case, it's not hard to show that actually in this case, the complexity it's the same. Okay, so so the more interesting case is when P and Q are independent. Then in this direction, so yeah, so yeah, so then in this direction, Fürstenberg in the late 60s have yes, some very insightful conjecture about numbers in independent basis. So he conjectured that if P and Q are independent, okay, so independent just means log P over log Q, it's a rational number. Then in this case, the orbit, the complexity of X in base P and in base Q cannot be both quite simple. In a more, what means simple? He gives a precise formulation. Yeah, so he asked, he conjectured that if P and Q are independent, then for every irrational number, we have either, the complexity of X and Y, the complexity of X in base P and in base Q should be, the sum should be at least 1. Okay, so this is a, yeah, it's quite deep conjecture, and it's still widely open. Yeah, so yeah, I will have not much to say about this conjecture. Now we know that this conjecture holds outside a zero-dimensional set of X. So but that's all. And of course, I suppose the real point is that this holds for all irrational number. So if we apply this conjecture to some classical constant like E pi, for example, 2 pi, then we can deduce that, for example, 2 and 10, base 2 and base 10, they are independent. So in this case, the Fürstenberg's conjecture tells you that, okay, so if you express your pi in decimal expansion or binary expansion, one of the complexity should be at least 1/2. Okay, so that's extremely strong if such result is possible. Okay. Yeah, so we can even go a little bit beyond this. So we can, in the same spirit of Fürstenberg's conjecture. So there are many different way of expand numbers. So you can use the periodic expansion, but then you can also use the quite classical continuous fraction. And then in this case, in the spirit of Fürstenberg's conjecture, so Fürstenberg considers times P and Q, P and Q, they have arithmetic independence. But if we consider numbers in periodic expansion, and then we also consider the numbers in the continuous fraction expansion, then in this case, we should also expect such kind of phenomenon, because in this case, if you take a number, you look at the orbit closure of X under times P, and you can also look at the orbit closure of X under the Gauss map. So in this case, it's related to the continuous fraction. We can also analytically define the complexity of X under this Gauss map. Then in this case, because the times P and the Gauss map, they have a geometry independence. So then it is probably natural to guess that in this case, probably there is also this kind of phenomenon. Yeah, so maybe, yeah. So of course, this is too ambitious as a conjecture, because, yeah, so it's just a dream. For example, if this is true, if you take the square root of 2, then we know that this is the quadratic algebraic number, and then we know that the continuous fraction expansion of square root of 2 is periodic. So in particular, this is 0, the complexity is 0. And if this conjecture is true, then this will imply that the square root of 2 will have full complexity for any base p. Okay, so this is, of course, this is a famous conjecture, but so far it's completely out of reach. So so this is probably another way to adapt this problem. Okay, so so let's return back to this orbit conjecture of Fürstenberg. So this has been quite open for a long time, and basically no much progress has been made. So in recent years, like more than 10 years ago or 20 years ago, so Fürstenberg asked a weak conjecture. So probably inspired by the recent trends of if you cannot prove the conjecture, a very hard conjecture, then you can prove that this conjecture holds outside a very, very small set of exceptions. So he asked if it is possible to prove that there exists an exceptional set of dimension 0, Hausdorff or Barton dimension 0, such that for all x outside this E, we have the conjectured conjecture conclusion. And as we will see, so this is now this weak conjecture. This is true, and this is implied by the intersection conjecture that we are talking about now. So let's see how to why this is two conjecture, why this orbit conjecture is related to the intersection of Cantor sets. So recall that we have this orbit, and now we take x, irrational number, and you look at the orbit closure of x, and we denote it by a, and the orbit closure of x under 3 by b, and suppose that this dimension of a plus dimension of b is strictly less than 1. Then conjecture 1, this orbit conjecture implies that x must be an irrational number, because otherwise, if it is not irrational, then it must be less than 1. Okay, and more generally, so this implies that a and b, all the points in a and b must be included in irrational number. Why? I'm also asking the question why. Okay, so yeah. No, this is not true. Okay, sorry. Okay, so this only implies x is a rational number. So okay, so that means that okay, yeah. Yeah. Anyway, I just want to say that the intersection should be small, but So I try to say it in a heuristic way, but since it seems like this doesn't work, so sorry. Yeah. Yeah.
You maybe apply A and set B being A intersected with B. Dimension. So A is less than 1 if dimension of A and B contain the orbit closure of anything in the intersection.
Yeah. Okay. Yes. No. Yeah. No.
Suppose the dimension of A is strictly less than 1.
Okay. Okay, so sorry, forget about it. I tried to use the heresy argument to relate it to these two conjectures, but okay, it's failed. So so the intersection is small. So the reason for this is of course because A is invariant by times 2 and B is invariant by times 3. So they have independent structure, so they should share not much structure. So so that's why they should be small and yeah. So actually, so this is a we can put it in a more general setting, and this is a Fürstenberg's intersection problem. So suppose that you have a dynamic system. I mean, you have a space X and you have a dynamic system F. So of course, our principal example in this lecture will be just this times2 map or times3 map. And then we can consider the invariant sets of this system. And if we can understand the invariant sets, then this we understand the dynamic property of this this map. Now, if we have two systems, F and G, and if you somehow want to compare these two systems, and then it makes sense to compare their invariant sets. And in particular, if these two systems, F and G, they are independent in some way, then it is expected that they should have few common dynamic structure between these two systems. And then we expect that the intersection of the invariant sets should be as small as possible. Okay, so here we should be more precise about what means independent and what means as small as possible. So the independence we have already seen. So if you like arithmetic independence, so times P and times Q, so P and Q is arithmetic independent. And we can also talk about the geometric independence, like linear map and non-linear map. So this is two such kind of independence. Yeah, so and about the as small as possible, Fürstenberg in his original paper already gives a formulation about this. So suppose now you have a dimension function, say the Hausdorff dimension, box dimension, or the entropy of this system, and in this case, Fürstenberg terms transversality. So two maps F and G are called transverse if for all F invariant sets A and all B G invariant sets B, we have the intersection of A and B have dimension bounded by this bound. So it's like the intersection have a dimension which is less than the when these two set in the generic position. Yeah. So that's the bound. That's the generic bound for two sets. I mean, if you take if you take two sets A and B, if you randomly translate or you randomly you randomly translate and rotate, then you have this. Then this is the generic bound. So Fürstenberg conjectures that in this case, this open bound should be always the correct bound for any such set A and B. Then he conjectures that for P and Q are independent, then the dynamics times P and times Q are transverse. Okay, yeah. So yeah, okay. So so now we know that yes, 8 years ago we proved that this is true. There are two independent proofs. One is by Bablu and one is by myself. So so actually we can prove a little bit more. So we can, not only by affine copy, but any C1 map, but that's So actually the interesting part is that these two proofs are quite different. So Bablu's proof is more of additive combinatorial natural. So he used yeah, so he used the method of additive combinatorics. Well, I will not. You will see the proof of bubble this afternoon. So my proof. Yeah. So my proof is. So I yeah, because when yeah, so when Fürstenberg asked this question in his original paper, he already gave a lot of interesting idea how to adapt this, and he also, in some special cases, he already gave a proof. So I just follow the idea of Fürstenberg and then add some steps and then complete the proof. So I'm more in the spirit of Fürstenberg's approach, and it's use ergodic theory, and yeah, so we will talk about the proof a little bit later. As a consequence of this intersection conjecture, then I mean, as a corollary of this, this corollary is actually due to Fürstenberg himself. So he can show that use this, one can show that there exists a exceptional set E with dimension 0, such that for all x outside this E, we have the Fürstenberg conjecture, orbit conjecture is true. The reason this implies this is you can, basically you can embed every invariant set times P invariant set embed into a self-similar set, which is P invariant or P to the power K invariant. And then we know that there's only countable many such kind of self-similar sets. And then if you take the union and the intersection, then yeah, so you do some calculations and you can conclude. I mean, you get this conclusion. Yeah. Okay. So yeah, I think I can give I'll talk about a little bit about the proof. So let's first start with the original idea of Fürstenberg. So we would like to bound this. Well, okay, so these are, bound this or the 0, but let's forget about the 0. So suppose that this is we want to show this kind of bound. But then the problem, the very easy observation is that this intersection is just a affine copy of this A times B intersect with this line, right? So now suppose that this is nice. So now we are consider this product set and consider this slice. So suppose that we have a slice of dimension S. Okay. Yeah. So that means it's the same as saying that you have a intersection with dimension S, and then we want to show that this intersection is less than dimension A plus dimension B minus 1. But for this kind of set, Cantor set, we know that the dimension of the product set is equal to the dimension A plus dimension B, just because those sets have equal Hausdorff and box dimension. So we only need to show that under this assumption, that there is a slice with dimension S, this product set must have dimension at least 1 plus S. So once we can show this, then we are done. Okay. Okay. So now we have a So now we have our set A and B. So this is our set A times B. So we have a slice, U E. So yeah. So and then now if we apply this times 2 and times 3. Okay. So now we are in the plan and we apply times 2 and times 3. Then, for example, we locate at one point on this slice, and then, for example, in this case, this small window will be magnified to a big one, and then it will be like this. Okay, so we can use the because those times 2 and times 3 they are expanding maps, so we can use this as a magnification to magnify, and then we can like continue this. We can repeatedly apply this times 2 and times 3. Then we get a sequence of sets, yeah, like this. So so every time you use times 2 times 3, well, yeah. Okay, so yeah, so yeah, of course. So here, not every time use times 2 times 3, but sometimes you use times 2, sometimes you use times 3 because this map is not conformal. So you want to keep this. You want to do it in a way such that so that the slope of the slice will not converges to some trivial limit. So you want to get yeah. So you just do it in a approximately conformal way. But for that you have a very natural choice. So you just use the irrational rotation. You just use the the irrational number log 2 over log 3 and do it appropriately using that number. So and then you get a you repeatedly apply these maps, and then you get a sequence of sets or a sequence of condition measures if you start with a measure. And the idea of Fürstenberg is look at this, consider this orbit of sets or orbit of measures as the orbit in some dynamic system, taking values in this probability measures, and then now if you take a limit of the distribution of this orbit, then you get a stationary distribution, and this stationary distribution is taking value on these measures on these kind of slices, and then yeah. So now and then and then taking into account that you use the irrational rotation on the slope. So actually, if you look at the whole system, so on the part A times on this product set, you have this magnification operator, and on this slope, you have irrational rotation about log 2 over log 3. And now this, now if you look at the marginal of this measure on these slopes, because this measure is invariant under the irrational rotation, so it must be the Lebesgue measure, and that exactly gives you that for and this tells you that for almost every direction you can find a slice with dimension s, and this is exactly so this is
the measure is in the projective space on the set of directions.
Yes, the marginal measure. That the marginal measure is on these angles. Yes.
I want to show that for almost every UZ,
yeah.
the intersection with A times B.
Yeah, dimension s. Yeah, they exist as slice. Yeah, yeah. So this, yeah, this is like so.
You apply for almost every U there exists. Okay.
Yeah, yeah. So this is like yeah.
What the invariance? Why would it make S appear?
Yes, That's very good. So it's not that simple as what you just described. It's still like you need to. So they are like factor J. Yeah.
If on every say line the dimension was exactly the same, then it can only be S. Something like that.
yeah. So you are talking about why this S appear, why it's 1 plus
I
S.
don't see the link between S and the Bergman.
Ah, yeah, no.
Like
Yeah, yeah, the S have nothing to do with the Lebesgue measure. Ah, okay. So I mean, yeah, I mean, even you start with just 1 point, you still get Lebesgue measure because, like, I mean, the slope of the, I mean, the slope of the slice will be, I mean, on the coordinate on this slope. I mean, the slope is controlled by this irrational rotation. So yeah, it's controlled by this irrational rotation. So it is invariant by this irrational rotation. If you look at the marginal measure of this system on this slope, then it is invariant under this by this irrational rotation. So it must be the Lebesgue measure. Even in the very beginning, you start just with 1 point. Well, of course, just 1 point. There's no slope. But if you start with any slice, you can always consider this as the slope. And but it is true that it's very important that we start with S, with dimension S, and S is strictly positive because the thing that if you want to, I mean, if you want to use the magnification, zoom in, and then if you are starting slice have 0 dimension state, then when you zoom in, then most of the times you will just see just 1 point probably. So if you have positive measure or positive dimensions, then when you zoom in and into different scales, you will see rich structures. And yeah, so that's yeah. Okay, so anyway, so this is this, I mean, the approach just I just described is due to Fürstenberg, and that was, yeah, quite an original idea. So so as a easy corollary of his results is that if you initially have a slice with dimension gamma positive, then for almost every direction they exist. I mean, for almost every direction there's a slice with dimension gamma, and yeah. So yeah, and yeah. So so now start with a single slice, then you get a rich family of slice. I mean, for almost every direction you have a slice with dimension S. So then you can, of course, ask the question. I mean, so now you have this set. In every direction you have a slice with dimension S. What's the dimension of this such kind of set? So this is some Fürstenberg type set. Nowadays, the dimension of Fürstenberg set it's very understood. So we know that in the general case, there's no. I mean, we cannot expect that such set have dimension 1 plus S. Actually, it is possible to construct Cantor example. But then, of course, in our case, I mean, in the Fürstenberg case, the slices they are actually quite regular. It's not like arbitrary set, but so those slices support measure, and those measure have rich dynamic structure. So it is still possible to show. I mean, to show that probably in this case you have dimension 1 plus S. Well, at least Babu tell me that just yesterday. So this is probably nowadays it's possible to show that such kind of spatial Fürstenberg set have dimension 1 plus S. Then that will give another proof of this result. But of course, 10 years ago we don't know this how to prove this. So we need to use other method. Yeah, so this is what this is in my proof how to do this. So this is the picture of Fürstenberg, and so what I have done is so try to show that there exists a subfamily of slices. They all pass through a small, extremely small ball. You just think that is 1 point. Still the slices passing through this small ball, they are well spreaded. Okay, they are pointed in, say, in almost every direction, or in a dimension in a direction of dimension 1. Yeah. So this is what. But once you have this kind of picture, then it's very easy to see that this set must have dimension 1 plus s. So suppose that all the slides have dimension s, and they all go through one point, and also they are pointed in sufficiently many directions, then you can conclude that the dimension of this set has dimension 1 plus s. Okay. Yeah. So so the way how to do this is so remember that we have our original system on this a times b, and also we have another coordinate is this slope. So but actually this is the skew product. So the problem is that if we know that our original system is like a Bernoulli, say, or sufficiently mixing, then if we condition on the orbit going into this small ball, and then in the same time we look at the slope, well, still we can make sure that this is equidistributed according to the Lebesgue measure. Sorry? Yeah, so this system is this system, yeah. So, okay, the slope, let's net by this S1. So, so you have T, and in the same time, you have also irrational rotation. Okay, so this T is the magnification. And
Rotation by log P or...
yeah, rotation by log P over log. So, yeah, thank you. Yeah. Okay, so if we know that the original system has, so it's Bernoulli, and if you look at those, we locate at this point and look at the tiny small ball with positive measure, and then we look at those orbit where those points will end to this small ball, and in the same time we look at the slope. If we know the original system is Bernoulli, for example, then we are happy because they will be still equidistributed, and you have those slides were separated in different direction. But of course, then since our system is we are taking the limit of some orbit, so there's no way to know the mixing property of this system. So, but fortunately, now it seems that this is quite easy idea. So fortunately, we have this, because we have this thinness factor theorem. So we know that our system contains a subsystem with the same entropy, and this subsystem is a Bernoulli. And of course, the price we need to pay is that the relative entropy, we need to take into account the relative or the fibers or the relative entropy. But in this case, since our original system projects to this Bernoulli system, but since the Bernoulli system have the same entropy with the original one, so the fiber has zero entropy. Or and since
So you take this system with what measure?
yes, this system is just so it's a measure. It's a measure we obtained by taking the limit of certain distribution of certain orbit. So that's the arbitrary aquatic measure, invariant measure. So so anyway, so because the relative entropy or the fiber is zero, so zero entropy, and our system is expanding. So this this corresponds to zero dimension in our set A times B, and in this kind of business, if you have a zero dimensional set, you can just think that this is 1 point. So and that's how we done this. Yes. It's a little bit complicated to explain all the details, but that's basically the idea. So yeah, I want to mention a little bit some recent or late development in this direction. So so there are now there are several different proofs of this conjecture. So I mean, as we said already in the very beginning, Pablo and I, we both gave a proof. So that's two proofs, and then later Yu Han gave a simplified proof. And this is in the case when dimension a plus b is less than 1. And then Tim Austin gave also a very nice and short proof, just using the original approach of Fürstenberg, but then cook up with some entropy technique. And then another important direction is try to generalize these kind of things into the high dimensional. There are different like Stuart, Yu, and the more recently this is a work of Pablo with Corso. Well, they gave a, I mean, in many cases, they gave a substantial generalization of this result in high dimensional situation. And well, I suppose probably we will hear about this more in Pablo's talk this afternoon. And there are also work of Joel and Glasscock and Richter, which generalize this kind of result into the setting of fractal sets in Z. So it's a discrete setting, but you can also define fractal sets in that setting. And then yeah, so there's also work, for example, in the very big, I mean, about the orbit conjecture. So there's some, yeah, as I said in the very beginning, so now we know that outside the zero-dimensional sets, this Fürstenberg's orbit conjecture holds, but beyond that, if we give a specific point, then irrational number, then this, yeah, there's absolutely no way to say about the, to know about the expansion in base 2 and in base 3, for example. And in this direction, there's some recent work, for example, Adam Zivsky, Faber Jung, about, so in that case, so it's yeah, so the proof that a number cannot be both extremely simple in the sense that if you have an irrational number, then you cannot be both automatic in base P and in base Q simultaneously. Sorry?
You cannot be, I missed the word.
Automatic sequence, yes. Yeah, yeah. Yeah, so that sounds, I mean, extreme, I mean, that's being a number being automatic in a certain base, that really means it's extremely simple. But still, that's a quite difficult, it's a quite hard task to show this.
Just saying one comment, because one can think that when you state the conjecture philosophically, one might think that the orbit of an irrational can not be dimension less than 1 in both P and Q, but that's not true.
Yeah, certainly, yeah.
Strictly less than 1 in both P and Q. It's just the sum of the dimensions.
Yeah. Only the sum of the dimensions. Yeah, certainly, yeah. Okay, so and finally, I would like to mention that this, yeah. So far, we are only talk about those sets which times P and times Q. Actually, we can. So those sets can be considered as a subset of certain self-similar sets, and this self-similar set, they have the same contraction ratio in the sense that if I set, we can, those times, for example, times 2 invariant sets corresponding in this case is when AI is 2 or 1/2, or the CJ is times 3 invariant state is CJ is 1/3. So far most of the work is so far one can only deal with the case when AI is the same 1/2 or 1 over P, and CJ is the same 1 over Q. But if we, I mean, those sets we call homogeneous self-similar sets. They have the same contraction ratio. But now, if you look at the case when this AI could be different, so say 1/2, 1/4, or 1/2 and 1 over 7, and the CJ could be 1 over 3, 1 over 5, for example. Then in this case, still they have independence. Then you expect that this will be still you expect the same kind of Fürstenberg phenomenon. But then it turns out that at least so far our method is not adapted to in this situation, yeah. So I mean, so in at least in our case, in our argument, we use it in an essential way, the irrational rotation. I mean, but now if we have different contraction ratio, then it's related to it's not irrational rotation, but then it's a multi rotation. So sometimes you need to choose rotate by alpha, and sometimes you need to. Okay. So sometimes sorry, this is late. Sometimes you need to rotate by alpha, and sometimes you need to by beta, and then how to choose this? It's arbitrary. So in this case, then the system it's difficult to control. But anyways, I think I'm ending, so maybe we can shut it down. So yeah. Yeah, so I just want to mention that in this no homogeneity, this is still a challenging problem. And yeah, so maybe I can stop here. Because, thank you.
Thank you very much. So any questions or comments?
Yeah.
What results are available for nonlinear setting? If maps...
Nonlinear setting, right? So even in this non-homogeneous setting, it's challenging. So in the nonlinear setting, probably it's even harder. So one of our initial approaches try to first deal with the no homogeneous setting, and then somehow try to use the no homogeneous to approach the nonlinear setting, because nonlinear is really like you can consider it's yeah.
Sometimes nonlinear can be easier.
Yeah, but so far, well, I don't know if Pablo has anything to say about this, but yeah.
I agree that it should be easier. I don't know how to do it.
So any other?
Yeah.
Very strange. Any questions or comments? No? So if not, let's thank the speaker again.
Thank you.